Cool, I'm audible. That's good. So hi, as said, I'm Josh. I work for these guys here in our Sydney office, and this talk is on my experiences in working with Haskell at Arbor over the past year. I find when people talk about Haskell, they tend to focus on the technical benefits, things like laziness, immutability, concurrency, and types, or they focus on the mathematical stuff, things like functors, monads, semigroups, and recursion, or they talk about the obvious thing, the fact that using Haskell gives you way fewer bugs. Instead, I want to talk about Haskell from a more human standpoint, the benefits to individuals, to teams, and to organizations, at least as I found in the last year of working with it. There's a kind of mind-blowing idea that occurred to me, probably during a particularly boring university lecture. Communication is the art of taking your ideas and putting them in someone else's head. However, like most ideas that people have in their early 20s, that's not actually particularly profound. Perhaps more profound is the notion that language gives structure to our thoughts. I personally think in English, it's not some intermediate representation that I put my ideas into, it's literally what I think in. And I suspect most people would say the same of their native tongues. Importantly, I think language shapes our thoughts. If something is difficult to express in language, we can find it much more difficult to form coherent ideas around that. And if something is inexpressible in the language, the ideas may never occur to us in the first place. So in that sense, programming is the art of putting ideas into the mind of a computer. In particular, it's the art of telling it how to do something. But it's also more than that. It's also the art of telling someone else, including your future self, what you want a computer to do. And it's quite important to make that distinction between what and how. Computers only really care about the mechanics. Until we get around to creating sentient AI, they're never really going to have a concept of intent. Conversely, people mostly care about what you want to do, what your intent with the program was. Because we can translate what into how, but it's much harder to translate how back into what. But programming is still more than that. It's the art of structuring your ideas of what you want a computer to do into instructions on how to do it, while still trying to retain enough of the what that somebody else can understand it. Or put another way, programming languages give us something to think in about what we want a computer to do and how we want it to do it. And of those three things, the particulars of how you want a computer to do something are probably the least important part. Vastly more important is that the how matches the what, and that other people on your team can understand both later. There's a wonderful quote in an old computer science textbook that's always kind of stuck with me. Programs have to be written for people to read, and only incidentally for machines to execute. I think programming languages have been gradually progressing in that sense. C was undoubtedly a leap forward over assembly, and languages like Python and Java were arguably leaps forward over C. But enough about epistemology for the moment. Let's talk about how we use Haskell at Arbor. For those who aren't familiar with Arbor, we're a company that works in the network security and visibility space. Our core products mitigate a wide range of cyber attacks, and they provide a way of seeing what moves across the network. The team I'm part of in Sydney takes summary data off our core products and transforms and enriches that so that our customers and our sales and support reps can get meaningful insights into it. Our main data set centers around all the cyber attacks we've seen, which goes back about 7 or 8 years at this point. This screenshot is from our Atlas tool, and it provides a way to explore the whole of our historical data set. And this one's from our digital attack map. It lets you see what's going on both right now and historically. I'm not really showing these to show off the products themselves. I'm showing them to show that this is Haskell powering real-world products. We're not doing research, and we're not some startup doing, Internet of crypto things. We're essentially using Haskell as a workhorse language for the same sorts of things you might use Java or Python. For us, that means that a data processing pipeline is a chain of microservices that typically talk to either Kafka and or S3. And once we've done all the transformations and enrichments, the data gets written into a database that powers our UI. We built and deployed our first Haskell service roughly a year ago. Prior to that, most of our services were in Scala, but almost all the new work we've done since then is Haskell. The story about how that first job came about is actually kind of unusual. There were 3 of us in the team at that point who were kind of new Haskell, and we were looking for something that was a good candidate to use it. We'd been beating our head against issue after issue implementing a service in, of all things, Python. And in a fit of annoyance, one of our programmers basically flipped the table, went home, and rewrote everything that was pissing us off into Haskell in an evening. And that ended up being our first Haskell in production service. Anyway, there are a few key points I want to make during this talk about what we've learned at Arbor in the past year. We've learned that Haskell facilitates clear communication, both to the computers and to your team members. We've learned that it facilitates clear and coherent thinking by giving you a consistent, expressive set of tools to work with, and by having those tools come close to letting you express what you want to do rather than how you want to do it. We've learned that it removes a large amount of cognitive load from programmers, allowing them to focus on the parts of their job that actually deliver value rather than on the mundane, error-prone mechanical details. We've learned that it makes good practice the natural things to do by making them the path of least effort. We've learned that it allows for agile decision-making by making change cheap, easy, and safe. And at the end, I'll also talk about some of the not-so-great parts. Now, most languages, Java, Python, C, and stuff, are very noun-oriented. They're oriented around things, around objects, around structures. And over the years and decades that programming has been a thing, we've developed some fairly consistent vocabulary around these nouns. For instance, almost all languages have some concept of a list or an array. There are only maybe 3 or 4 significant variations across languages, and both what you use them for and how you use them tends to be pretty consistent. Instead of being concerned with memory and structure, a programmer can think in terms of a list of things. And that thinking is transferable. How you think about a list in one part of your code tends to be fairly similar to how you think about a list in another part of your code, or even how you think about them in another entirely different program in a different language. And that means that thinking can be reused. And that's really important. It means we can think and express ourselves and communicate on a higher level than if we had to deal directly with memory and offsets and pointers. That also means that when you're reading code from another programmer, your thinking and their thinking will tend to match. They transferred some notion about what something should do and how it should do it via code to you. The same principle can be applied to other things. Almost all languages have some sort of key value map, they have some sort of set. And that's great because they give us a way to communicate in concepts rather than implementations. Similarly, object-oriented patterns like factories and adapters and observers give us a way to communicate about architectural designs. In fact, I'd argue that at this point we've mostly succeeded in creating a common vocabulary of programming nouns. We've worked out most of the complexities there, and we've extracted most of the value that's there to extract. But I don't think you can build a programming language only out of nouns. In fact, and I don't think we've done so well in creating a consistent and expressive programming vocabulary of verbs, or actions, or whatever you want to call them. Most languages have some variation on if, then else, for, while, try-catch, functions, methods. Most of them have classes these days. And those mechanisms are both general and composable, which is good, but they're also really primitive. They're much more oriented around telling a computer how to do something than on telling it what you want it to do. Once you go beyond that, things tend to get quite inconsistent. The way you work with lists and arrays tends to be quite different to the way you work with sets, which is often different to the way you work with maps. And even in languages that do get those right, once you get into more complex domain-specific stuff or into third-party libraries, you quickly start to find inconsistencies. The key insight we've had about Haskell is that to really productively express yourself, to both express what you want to do and how you want to do it, you need a consistent, expressive, composable vocabulary of verbs as well as the nouns. Simplest example is a straight A to B transformation. Suppose I have a relatively simple function. It takes some bread and returns a burger. Fairly straightforward. But real programming is rarely that simple. For instance, perhaps the bread is moldy. If it's not, I still want to make a burger. But if it is moldy, I just want to leave it alone and deal with it later. Or perhaps I have a loaf of bread and want to make a lot of burgers. Or perhaps I'm out of bread. Whether or not I can make a burger depends on whether I have any bread. Or perhaps I send someone out to the shops. In the future, I'll have bread, so in the future, I'll be able to make a burger. In most languages, how you'd apply that transformation would depend heavily on the context. In Java, for example, you might end up using a try-catch for the moldy bread, a for loop for the loaf, an if-then to check if you have bread, and a continuation if you need to get it from the shops. In Haskell, we have the same consistent vocabulary throughout. I just map my toBurger function over whatever context the bread is in. That frees up both time and thought power. You don't need to think about how to do that transformation, or what the appropriate control flow is, or what the edge cases are, and you probably don't need to look up documentation or examples. It's also much clearer and more explicit in terms of communication. Instead of needing to read and understand what a particular block of code does implicitly, the code explicitly states that it's doing a particular type of transformation. Ambiguity and misunderstanding are far less likely. Mapping transformations are probably the simplest example, enough so that many non-functional languages are starting to pick up that concept. However, the sheer breadth of things that concept alone can be applied to is pretty incredible. At Arbor, we're using this for streaming, parsing, error handling, missing values, I/O, async, generating test data, functions themselves, as well as the obvious things like lists, sets, maps, and strings. And that's far from exhaustive. It's really only Haskell and sometimes Scala that explores the full breadth of what's possible here, at least out of the languages that I've used. That's certainly not the only consistent piece of vocabulary in Haskell either. Things like filtering, aggregation, accumulation, and joining are all fairly consistent across both the core and the third-party libraries. In addition to those, anything you might reasonably consider a numeric type will probably have all the usual mathematical operators defined for it. Accessors, what you'd call getters and setters in most languages, are all generally quite consistent thanks to lenses. And working with things like application configuration, shared state, logging, monitoring, and AWS is all fairly consistent and pains-free thanks to monotransformers. The other big aspect of Haskell that really helps, both in terms of how you think through programs and how you communicate that thinking to your colleagues, is in a way it forces you to be explicit about almost everything you're doing. Probably the most well-known example of this is I/O. It's almost impossible for a function to have an effect on the outside world without that being reflected in its type. If you need to make a database query or talk to AWS or log something to standard output, then your function's type will reflect that. That means it's impossible to miss when a function is having a side effect. The fact that you can't escape from I/O, by which I mean you can't get rid of that particular type annotation, means that you also can't ignore it. You have to deal with it. It's like a big neon sign saying, be careful, both to you and to anyone else reading your code. It's not just I/O though. Haskell's conceptual equivalent to nulls is always represented in the function's type. And you have to deal with the potential lack of value before you can get at the actual data, which means no more null pointer errors. The corollary to that is that if a function's type doesn't say it might return something, then you'll definitely get a usable value back. So not only do you not have null pointer errors, you get to stop worrying about them or feeling guilty about not checking for them at every single object you reference. The same principle applies to other types of errors. They're always represented in the type, you have to deal with them, and if it's not there, you don't need to worry. As a bonus, there's no syntax level try-catch finally. Errors and error handling are just regular values. But we can go even further than that. This is a snippet from our code base at Arbor. It builds a Kafka producer the way we need it. The actual implementation isn't important here. What's interesting is the type signature. Essentially, what we're doing is putting constraints on where in the code we can make a Kafka producer. The first constraint, monad resource m, says that you can only make one in a context that can allocate and clean up resources. The second one, monad reader rm, says that you can only make one in a context that provides access to a read-only environment. And the last two say that the read-only environment has to contain enough information to configure Kafka, and it also has to contain a logger, respectively. One nice side result of this is that it lets you be really specific about the sort of things you need from application environments. While a function can access our Kafka config and the logger, it wouldn't be able to access something like AWS, even if that was also in that environment. That lets us really clearly communicate what we're doing, both to the computer and to other programmers. Best of all, both the implementation and the usage are checked at compile time, so if you do try to do something or use something you're not supposed to, you know immediately. Now, I said this was about the human side of Haskell, and I want to re-emphasize that. What the explicitness and the expressiveness and the consistency of Haskell really gives you at the personal and the team level is confidence. When you ask yourself, am I missing an edge case here? The answer is almost always no, because your edge cases are stated explicitly with types, and in most cases, they're dealt with for you automatically by those types. And when you're trying to think through the mechanics of how to solve a problem, there are almost always existing tools that explicitly do what you need. You rarely end up second-guessing whether you're using the correct thing or whether you're using the thing correctly. And when you read code that somebody else has written and ask, do I understand this? The answer is usually yes. Because most Haskell code works by directly stating what you're trying to do, rather than by having that be a side effect of how you're doing it. And those three things, confidence in your code, in yourself, and in your team, allows you to be making progress almost all the time. But even in Haskell, sometimes you need to go back and rework something. In most languages, refactoring code is laborious, it's error-prone, and it's mentally tiring. You have to keep large chunks of code in your head at once. You have to track all your side effects, both internal and external. For example, changing a shared variable or making a database call. You have to ensure that you're not violating some non-obvious property of code that a different area of code depends on. And you have to track all your edge cases to ensure that you don't miss ones that you were previously covering. Even with languages that provide a lot of support for this, Java and IntelliJ, for example, large-scale refactoring is often seen as too time-consuming and too risky a proposition to be undertaken. Refactoring in Haskell, by contrast, is enjoyable. It's easy. It lacks most of the entirely justified paranoia that you usually get in other languages. It's fairly common for my team and I to rewrite large, critical regions of code, and for those to work the first time they pass the compiler. The cause of that is a combination of a few things: the strong type system, functional purity, immutability, and a few other minor niceties. But what's important is that when you put all those things together, it removes the fear and the risk. You stop feeling like you're boxed in by previous decisions, or the ones that you're currently making will box you in the future. And once you're comfortable working like that, refactoring stops being something that you avoid and instead becomes just another tool in your toolbox. You become much more comfortable writing something you know will need to be reworked, or okaying similar work from your colleagues, because that rework isn't going to be a burden to you. Perhaps the nicest upshot of this is that it allows you to defer both architectural and business level decisions to much later in the development process. Software architecture in particular is one of those areas where being agile has never really worked because changing architectures is usually a long and expensive endeavor. But Haskell gives you a lot of flexibility in that regard. On the business end, while we occasionally have to tell our product manager that an idea won't work, I don't think we've ever had to tell him that something was too hard or too complicated or too risky. Using Haskell means that we can confidently respond to change. It allows us to be agile in the original sense of the word before all the consultants got to it. Now, designers will often tell you that the best user experience is the one you don't notice, or the one you don't have to think about. A good design naturally guides you to the correct way to use it and makes incorrect ways unnatural or outright impossible. The same principle applies to programming language design, and from this perspective, Haskell is arguably one of the best languages currently in use. It's also arguably one of the worst, but I'll get to that in a bit. The two most obvious examples are function purity and immutability. Those are both good practices in almost every language, but they're frequently ignored for the sake of either convenience or efficiency. It's much nicer to have those be the default than to have to put in the extra work and the extra thought to get them. Only slightly less obvious is the fact that it's typically simpler and easier to handle edge cases in Haskell than not to. And the compiler will often warn you when you miss some. On the larger end of things, the most natural way to structure a Haskell codebase is with large, loosely coupled core of pure functions, a compositional layer that brings together that core functionality, and a thin wrapper of impure code that talks to the outside world. In object-oriented terms, you'd probably call that a ports and adapters architecture, or maybe a hexagonal architecture. Those are typically something of a Sisyphean task. They take consistent effort and diligence to maintain, and you can quite easily backslide into bad design. In Haskell, you have to work quite hard not to achieve that sort of architecture, at least accidentally. And that's the thing. For most questions you might ask in terms of what's the best way to do this, the answer is usually whatever seems most natural. And when you do get it wrong, it's easier to refactor anyway. Now, I said I was going to cover some of the not-so-great parts. Haskell's probably biggest, most glaring issue is that it's got a learning curve like a brick wall. But I'm not actually sure that's because it's hard. My university used it as a teaching language in their intro programming course. And in the 3 years I taught that, most of the students seemed to get it, at least to the level that we were teaching them. In fact, it was usually the students who had done programming before that had the most trouble. They kept trying to program the way you would in C or Java or Python or whatever they knew, and that really doesn't work in Haskell. We noticed something similar in our office. we ran some internal training to bring the rest of the team up to speed. And some of the people coming from JavaScript or C++ backgrounds took to it like ducks to water, whereas some of the people who were actually coming from things like Scala struggled. And that's probably the key insight in terms of learning and teaching Haskell. It has so little in common with other programming languages and with other styles of programming that most of what you know won't help. Possibly worse, there are some bits that actually are similar, but are subtly different, and those can be really frustrating. Much like trying to learn Vim or Emacs when you're coming from editors like Visual Studio or IntelliJ, or trying to learn to play Dwarf Fortress when you're used to Overwatch, the best thing you can do is forget everything you know and learn from scratch. I was lucky enough to come into the team already knowing a decent amount, but even I have had days this year when I'm faced with yet another mind screw of a library, I just want to pack the whole thing in and go back to Python. All that said, I think once you do know Haskell, it's a vast improvement over the usual C and Java style of programming, both conceptually and syntactically. Probably Haskell's other big problem, at least on a human level, is how much of a blow it can be to your self-confidence at times. In other languages I've worked in, you spend 3 hours, you write 30 or 40 lines of code, you do the same in unit tests, it all mostly works, and you pick up a few issues in code review. You feel pretty good about yourself, you feel pretty productive. In Haskell, you spend the first hour just trying to wrap your head around some esoteric concept. You spend the next hour slowly hacking out 5 lines of code, mostly just by following the type errors rather than understanding what you're doing. And then the third hour, refactoring that down to a 2-line expression, which you can't really unit test without re-implementing it anyway. And then you get to code review, and your colleague tells you that the thing you wrote is a one-liner in some library you've never heard of, and you feel like an unproductive idiot. And it's days like that you really have to remind yourself code is a liability, not an asset, and the less code you write to solve a problem, the better off you are. I also think it's really important to call out these difficulties, partly because it means we can work to fix them, but mostly because I think it humanizes Haskell and the people who write it. There's a perception, particularly outside of the FP community, that Haskell is this academic ivory tower sort of thing, and you have to be some brilliant PhD to write it, and that all the regular programmers should, stick to down-to-earth practical languages. I think that's a load of rubbish on all counts. I don't have a PhD, and I'm definitely not a genius. My last job was writing Python and JavaScript, and it took me like 4 or 5 attempts across a number of years to be able to understand monads. And you could say similar things to most of the people on my team. Every one of us had problems getting started, and we all have days when we struggle. Ironically, we do have a few PhDs at Arbor, and I think they all write JavaScript. You can interpret that however you want. What I am continually surprised by is how practical and people-oriented Haskell actually is versus what I expected. And that's probably the key takeaway from this talk. Selling programmers on the technical benefits is relatively easy. To convince skeptics and management, you have to sell it to them on the human side. Anyway, that's my talk. Does anyone have any questions?